Alright guys, this the second example under non-exact differential equation. Of course, we have solution. Let's see what we're going to have here. So m, as usual, m is equal to y is to the power 4 plus 2y, and our n is equal to xy³ plus 2y raised to the power 4 minus 4x. So we're going to differentiate this guy with respect to y. Differentiate with respect to y definitely will give us 4y raised to the power 3 plus 2. Then differentiating this guy with respect to x. In this case, differentiating x is 1, so we have y³. This is y is 0 because it doesn't contain x, and differentiating 4x is 4. We have minus 4 here. So it's evident that partial differentiation of m with respect to y is not equal to the partial differentiation of n with respect to x, which shows that it's not exact. So we're going to find the integrating factor. Finding the integrating factor mu. Finding the integrating factor. Then we have to check if f of x has to be equal to f of x has to be equal to partial differentiation of m with respect to y minus partial differentiation of n with respect to x all over n. Then let's check if this particular equation results to a function of x alone. So the partial differentiation of m with respect to y actually give us 4y³ plus 2 minus the partial differentiation of n with respect to x definitely give us y³ minus 4 all over n, and of course our n is xy³ plus 2y 4 minus 4x. Definitely this can never give us a function of x alone. It can never give us a function of x alone because these values here can't be factorized. If you want to go further, we're having something like 4y³ plus 2 minus times y is minus y³ minus plus 4 minus into negative 4. We have xy³ plus 2y raised to the power 4 minus 4x. So this is not giving us a function of x alone. 4y³ minus y³ is actually 3y³ plus 6 up here, and we find out that the function we have is still a function containing both x and y. Definitely this is not going to be a function of x alone. Alright, so we are going to check the second alternative. f of y has to be equal to partial differentiation of n with respect to x minus partial differentiation of n with respect to y all over m. So let's check if this one works out. The f of y will be equal to the partial differentiation of n is y³ minus 4 minus the partial differentiation of m is that's 4y³ plus 2 all over m, and of course our m here is equal to y or 4 plus 2y. Is that okay? So we have this equal to y raised to the power 3 minus 4 minus times 4y, it is in 4y³ minus and minus times 2 is minus 2 all over, of course, what we have here is y raised to the power 4 plus 2y. Is that okay? So watching this now, y cubed minus 4y cubed definitely will give us minus 3y cubed minus 6, right? All over y raised to the power 4 plus 2y. As you can see, we are actually having a function of y alone here, yeah, which is a function of y alone. We can actually factor out 3 from up there. You can see this minus 3 into 3 is common. Yeah, 3 is common. We have y cubed here plus, due to this negative here, we have y cubed plus 2. So that minus 3 times y will give us this, minus 3 multiplied by 2 will give us minus 6, all over. Then factor out y from here, y into, we have this is y cubed plus 2. As you can see, we have the same thing up and down. This guy can cancel this, so we have the value to be minus 3 over y. So we have our f of y now is equal to minus 3 over y. So we can go ahead to find our integrating factor mu. Integrating factor is equal to an exponential integral of f of y with respect to y. So we use that particular function of y to find the integrating factor. Alright, to find the integrating factor, we have mu is equal to exponential integral of f of y is minus 3 over y with respect to y, which is equal to exponential minus 3 exponential minus 3 integral of 1 over y dy, right? And that's bringing out the constant at behind the integral notation. Then integral of 1 over y will give us ln y. So this is equal to exponential minus 3 ln y. Right? So we can take this minus 3 to go to the front according to the law of logarithm back to front law. Then the integrating factor is equal to exponential ln y raised to the power minus 3, and definitely this is equal to exponential logarithm of exponential function by x raised to the power minus 3, which eventually gives us the x raised to the power minus 3 as the answer, which is the same thing as 1 over y raised to the power 3. So this is our integrating factor. We're going to multiply both sides, multiply the given equation by this integrating factor in order to make it to be exact. Alright? So this is our given equation. We have the integrating factor is 1 over y cubed. 1 over y cubed times y power 4 plus 2y dx plus 1 over y cubed by xy cubed plus 2y4 minus 4x dy equal to 0. We have y raised to the power 4 divided by y cubed will give us y. Will give us y equal to y plus 2y divided by y cubed will give us, of course, y divided by y cubed is y squared, so we have 2y raised to the power minus 2, that's 2 over y squared, all dx plus xy³ divided by y³ will give us x, and 2y4 divided by y³ will give us plus 2y, minus 4x divided by y³ will give us 4x, y raised to the power minus 3 dy equal to 0. Okay, so we can call this one n. N is equal to y plus 2y raised to the power minus 2, and that's m. And n is equal to x plus 2y minus 4x, y raised to the power minus 3. Okay? So we are going to differentiate this with respect to y and this with respect to what? X, to know whether if the equation is now exact. So the partial differentiation of n with respect to y is actually for differentiating y here is 1. And of course, differentiating 2y raised to the power minus 2, minus 2 times minus 2 times 2 give us minus 4y. Removing 1 from the power give us minus 3. And then partial differentiation of n with respect to x is equal to differentiating x with respect to x is 1. We jump this guy because it doesn't contain x, and differentiating x here is equal to 1. And what we have left here is minus 4y raised to the power minus 3. And if you take these two equations, you find out that it is evident that the equation is now exact. So we have partial derivative of n with respect to y is equal to the partial derivative of n with respect to x is now exact. Now, there is a function z x, y such that partial differentiation of z with respect to x is equal to m. Then integrating both sides, we have z, the integral of changing z is z, that's partial derivative of z will give us z of x, y equal to integral of m with respect to x with a constant which is a function of y. So z is equal to integral of m, and of course the m we're using this m is equal to y plus 2 y raised to the power minus 2 all the y all the x plus c of y. Okay, so we're going to integrate this function now so that we have z to be equal to integral of y with respect to x is xy. You add this, and y is considered to be a constant, so integrating a constant will add a variable because it's with respect to x. Integral of y is xy. Integral of 2xy squared is 2. Integral of 2y raised to the power minus 2 is 2x y raised to the power minus 2 plus c of y. Okay, so this is our major equation, but we're going to go for c of y to evaluate c of y and add it to the equation. Okay. All right. So there exists also partial differentiation of z with respect to x to y now equal to n. So differentiating this our function in order to evaluate c of y, where z is equal to this function here, we have partial differentiation with respect to y. Of course, our z is this function here. We have xy plus 2x y to the power minus 2 plus c of y equal to n, and of course n is equal to x plus 2y minus 4x y raised to the power minus 3. Okay, so differentiating this guy with respect to y, differentiating y here is 1, we have x left here. We are differentiating this guy with respect to y, minus 2 we multiply this guy will give me minus 4x is constant, x is constant, repeated. Then removing 1 from the power of y, we have minus 3 plus differentiating c of y, c prime of y. And that's equal to x plus 2y minus 4x y to the power minus 3. So we can remove this guy from both sides because it appears and remove x from both sides so that we have c prime of y is equal to 2y. Okay? Then to make c of y the subject, we integrate both sides so that we have c of y to be equal to 2y squared over 2 plus k, so that c of y finally is equal to y squared plus k. So since we've known the value of c of y, we can now substitute in this major equation so that we have our answer. Therefore, z is equal to xy plus 2x y raised to the power minus 2 plus c of y, and c of y is equal to y squared plus k. Taking k to that side, we have z minus k is equal to xy plus 2x y raised to the power minus 2 plus y squared. Then replacing z minus k with a constant a, we have xy plus 2x y raised to the power minus 2 plus y cubed, where z minus k is equals a. So that's the solution to the differential, non-exact differential equation.